What's up, everybody? Welcome to lecture 21. It is over section 4.1 and 4.2. So the way this lecture is going to work out is I'm breaking it up over two videos. And the reason why is because, well, my own sanity, as well as y'all's sanity. This covers a lot of material, a lot of new notation, and there's a lot of nuance to it. So I thought it would be best to really break this video up into, like I said, two different parts that kind of hit on the big topics within these two sections. So, having said that, there's some new notation we need to introduce. This thing. And to answer the question on the board, no, you cannot send it back to the upside down, though I'm sure 11 did try. Anyone who understood that reference, you just passed. Everyone else, you just failed. No, so what this thing is, it's just a fancy way of saying do a bunch of addition. And it encloses all the rules for how you're supposed to do that addition, all in one nice condensed package. That's it. That's all that's happening here. So, what we are saying is we are going to take the sum of f evaluated at x sub I from I equal to k to I equal to m. That's all. I know. I say that's all, and it's like, you didn't really tell me anything here, Matt. You're right, I didn't. I just read it to you. So what this thing is doing is it's saying we have a particular rule for how we're going to pick each term. And then we're just going to add up all those terms. The rule is whatever your function is, right? Whatever that equation, I should say, is. And it tells you where you're going to start and where you're going to end. So functionally, one way that this can be understood is with a simple example like taking the sum from I equal to 3 up to, let's say, 7 of I. So what this is saying in condensed notation is you're going to take 3 plus 4 plus 5 plus 6 plus 7. That's it. That's pretty simple, right? Now, another way to see it is with another example. Let's say this is from I equal to 0 up to, I don't know, let's say 5. And we want to use I squared plus 2. Actually, let's use I squared plus pi. Well, this is saying you're going to take 0 squared plus pi plus 1 squared plus pi plus 2 squared plus pi plus 3 squared plus pi plus 4 squared plus pi, and finally plus 5 squared plus 5, or plus pi, sorry. That's all it is. So in this example, or in these two examples, here we're saying f of x sub I is equal to just I. And here we're saying that f of x sub I is equal to I squared plus pi. So really, what this x sub I is doing then It's just saying how you're gonna, that you're picking particular x values. It's not all the x values, it's particular types of x values, right? In other words, in this case, x sub I could be thought of as being equal to I. And here, x sub I is equal to I. So we're saying we have a collection of possible x values. Now you're going to break them up and order them. You're going to organize these x0, x1, x2, x3, x4, x5, so forth and so on. And those x values, those x sub I values, are going to obey a particular rule. So this is saying the first x value is just going to be equal to 1. The second x value is just going to be equal to 2, so forth and so on. Have the same thing happening in this example down below. That's really all this is. Now we're going to get fancy with it. We're going to use it in other ways. And I'm going to show you a couple series, which I'll explain that term in a second. A couple series that have very well-known, well-understood properties in conditions of convergence. So before I go on to any of that, I need to explain what a series is. This is a series. Wow. I know, right? Kind of dope. It is not the mind flare that it looks like. No, this is what's called a series. And if a series converges, what we're saying is that the sum goes to a particular value. Well, it seems obvious with something like these two that they would converge onto a particular value. But what if we had a series that adds up an infinite number of values? Well, yeah, sometimes actually those do converge. We're going to have a bunch of examples of those after a while. But on the other hand, when we have a series that does not converge onto a particular value, we say that it diverges. So these two series converge. They're finite. Their answer is a nice number. That's what it means to converge. If they did not converge, we would say these series diverge. So we have an idea of convergent, divergent, and of what's called a series. These series could have a finite number of terms, like these, or they could have an infinite number of terms. Now, one more catch to all of this. The type of infinity we're talking about is the countable infinity. And that's something for a larger conversation, the difference in different type of infinities. But we have a countable infinity. That's the infinity you could say 1, 2, 3, 4, and in theory count 2. And then we have the other type of infinity, which is the uncountable infinity. And that's the infinity that occurs between within intervals. So for example, the total number of values between 0 and 1 is uncountable. Okay, well that kind of makes sense because you can't count all the numbers between 0 and 1. Even if you could, in theory, live forever, you would not be able to count all of those. And just to see that, think about all the numbers between 0 and 0.1, let alone all the numbers between 0 and 1, let alone all the numbers between 0 and 0.05. And we keep going down and down and down. All of those have an uncountable number of values in between, right? So here we're going to be dealing with countable values. And that makes sense because if you're putting things together in a series, in theory, you can count them, right? So there's that. Having said that, you're probably wondering, why the hell do I even care about this thing? That's a good question. Why do you care? Well, you care because we're going to use this notation and these ideas to talk about the area underneath the curve. And in a little bit, we're going to find out that these things, these areas underneath curves, are really deeply related to the idea of the derivative and are a form of an integral. The idea that we're going to be talking about is called the definite integral. So, having said all of this, I should take a moment to pause here and tell y'all you should go look at your notes. In the first 6 or so slides of your section 4.1, 4.2 notes, there are slides that explain the relationship between slope and area. And it does it in a nice, crisp, clean way. I'm not going to be able to get to it in this lecture video or in the next lecture video, but it would be a very, 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 very good bonus question for me to ask. I'm not going to promise you I'm going to ask it, but it would be a good bonus question. What's the relationship between area and slope, area and the derivative? What's going on with these? And asking you to explain them. And I say it would be a good bonus question because it gets at the understanding of this idea. So, having said that, I think we're going to get on with it. Alright, so how are we going to use this? Well, start off with, let's imagine we've got this function here. We want to know what the area underneath that function is between x equal to a and x equal to b. Well, first, we could use what's called the definite integral from a to b of f of x with respect to x to find that area. That's what that notation is. It's the definite integral. It has a lower bound a, an upper bound b, and f of x is the function that we're integrating. X is what we're integrating with respect to. We could do that, but right now we have no clue what that is. Like, we don't even know what we're looking at over there, right? So instead, why don't we try to approximate it? And why don't we try to approximate it by taking and forming a bunch of rectangles that tell us something about our function, using those rectangles to find an area that's approximately equal to something related to our function, to the area underneath our function, and then adding all of those up. So what I mean to say is, let's take our function and our interval from x equal to a and x equal to b. That is x equal to a there. That is x equal to b here. Let's break this interval from a to b up into 4 equal parts so that the length, or rather the width of every rectangle will be b minus a divided by 4. That is to say, each of these will have the same width, and that width, in this particular case, is b minus a over 4. Now, we have to decide how we're going to pick the height of our rectangles. In this particular case, I said, you know what? Let's just set the height of the rectangle so that the left-hand corner, the top left corner of each of our rectangles is equal to our function. So, the left-hand side here is f of a, and over here this is going to be f of b minus delta x. Because b's over here, we're going to go 1 delta x to the left to get to that top left-hand corner, and we want that to be the height of that top left corner to be equal to our function at that particular x value. That particular x value is b minus delta x. Now, this is a little bit weird, and I'll explain why in a second, because we're going to abandon this in a minute and just work with our delta, or just work from f of a and with our delta x's. So what I mean to say is, another way of writing this is to say, all right, if this corner here is at f of a, then this next top left corner is at f of a plus delta x, because we only go delta x over, right? So we're going delta x to the right. Then this top left corner over here for our third rectangle will be f of a plus 2 delta x. And finally, our last rectangle, the top left corner of it, will have a height of f of a plus 3 delta x. Now, what we're going to do is we're going to take the area of each of these rectangles. This particular far right rectangle is going to have an area of, well, the height of the rectangle is f of a plus 3 delta x times the width of that rectangle, that's just delta x. The second to last rectangle has a height of f at a plus 2 delta x, that quantity times delta x. Our second rectangle has a height of f at a plus delta x, all that multiplied by delta x. And finally, our first rectangle has a height of f at a and a width of delta x. And that gives us the area of all 4 of those rectangles. Now, we're going to add all those up to approximate this area. So adding all of those up, we have f of a times delta x plus f of a plus delta x times delta x plus f of a plus 2 times delta x, that quantity times delta x, and all this plus f of a plus 2 delta x, all of that times delta x. Well, hey, check it out. What we've got here is something that we could condense into a lot smaller notation, because we're applying a particular rule for how to evaluate our function, aren't we? And then we're just doing the same operation over and over and over beyond that, really. So what I mean to say is we could use that series notation to say this is equal to the sum from, I'm going to use a different variable, or different dummy index. Instead of I, I'm going to use m. From m equal to 0 up to m equal to 2 of f of a plus m times delta x, that quantity times delta x. So this is how we're going to use this notation. Now check it out. That is approximately equal to the area, which we said is equal to this thing, the definite integral, from a to b of f of x dx. Now I should remind you, delta x, in our case, we said is equal to b minus a divided by 4. Notice, we got the 4 because that's how many rectangles we have. B minus a because we're starting at a and going over to x equal to b. Excuse me. So, if we want the width of each of these rectangles to be equal, then we have to take that distance of b minus a and divide it into 4 equal parts. That's why delta x is equal to b minus a divided by, in this case, 4. Okay. Well, let's take a minute to think about what would happen if we were to shrink these rectangles in width. That is to say, if we were to use more rectangles, if we were to pack in more rectangles between A and B. They all have to be of equal width. But as we do that, our approximation should get better, right? Sure, because check out what's going on up here. In this picture here, this rectangle is overshooting our function a little bit. This rectangle is overshooting our function a little bit. This rectangle has an area that's undershooting a little bit. And this rectangle has an area that's undershooting by a decent amount. And we can minimize that error by using smaller and smaller width rectangles, couldn't we? Think about that for a couple seconds. Now, think about what it is I'm implying here. Talking about just throwing a bunch of rectangles into this. That sounds a whole lot like letting the numbers of rectangles approach something, right? I'm saying you're going to increase the number of rectangles. You're going to increase them again, and you're going to increase them again, because every time you increase them, your approximation, this approximation, will get better and better and better, right? Again, we're approximating the area of this, right? Of this pink bit here. So, with more rectangles, finding those areas and adding them up, our approximations will get better. So much so that if you could do that an infinite number of times, you would have zero error. Zero. None. Zip. Zilch. Wait. So that means then this thing is equal to the limit as the number of rectangles approaches infinity of all of this. So let me write this out. We're going to say we have an upper bound of k approaching infinity of the sum from n equal to 0 up to k of f of x sub I. I'm going to write it like that. I'm going to write it like this. A plus n times delta x, all that times delta x. Where delta x is equal to b minus a over k. Holy shit, that looks like a mess. That looks worse than a mess. That looks like a nightmare. Legitimately something from Stranger Things. I promise it's not that bad, guys. In fact, you actually already know how to do this. You may not realize it yet, but you will in a little bit. Now, that's cool and all, but it does us no good unless we use it. So guess what? It's time for some examples. So really quick before we get into those examples, I just wanted to rewrite what I had just written, because I figured it probably wasn't the easiest to see down there at the bottom, kind of just scribbled in. But what I am saying is the area underneath some curve between x equal to a and x equal to b is equal to the definite integral from a to b of f of x with respect to x. And what that thing is the limit as k goes to infinity of the series from m equal to 0 up to m equal to k of the quantity f evaluated at a plus m delta x times delta x. And that all of this is approximately equal to that same series, just without the limit. So here, k is just some finite value. It's just some number, and that's it. This stuff's pretty cool, actually. I like this stuff. Analysis is great. What else did I want to say about that? I think that was all. So now we're going to go to the examples. 2. Okay, I lied. We're back. We're not going straight to another example because there was one last thing I wanted to talk to y'all about. What I wanted to talk to you about was the idea of a Riemann sum. This is an example of a Riemann sum. This is what's called the left-hand Riemann sum. There are right-hand Riemann sums, and there's what's called the midpoint rule. Sometimes called the midpoint Riemann sum. I almost never hear it called that, but I've known a few people to call it that over the years. What a Riemann sum is, and what this thing properly is equal to, I'm going to erase this. Cool. It's actually, once I write all of this down, there delta x is always going to be this thing. So, what a Riemann sum properly is that same sum, but we're going to replace everything inside of the function. And what we're saying here is that there's a particular rule we could apply to choosing our x star sub n. Xm sub star or superstar, how? You know what I'm trying to say. That x sub n star value. There's a couple different rules we could use. We could use the left-hand rule, the right-hand rule, or the midpoint rule. All three of those are in your notes. I do not know the exact page. I don't know the page because these are not numbered. Awesome. I was an idiot when I did that. But you should go back to your notes and look at them. I just simply don't have time to delineate through all of those examples. One, you're not going to watch that part of the video. I know this. I know y'all. Y'all know this. I'm happy we're all in agreement about that. And two, I think the notes make it a little bit more clear what's happening here. We're just going from either the left-hand side, or we need to move one side over and have the height of our rectangle, the height of our rectangle based on the top right corner being equal to the height of our function, or we could use the midpoint. That's really all the differences between these three rules. Setting the top left corner equal to the height, the middle of the rectangle equal to the height, or the top right corner equal to the height. That's what these three rules do, is they move between those three cases. What else did I want to say about that? That was all. Now we're going to go to some examples. Cool. Okay, so for our one and only example for this video, what we want to do is we want to approximate the area under the natural log of x from 1 to 5 with respect to x. We want to approximate that area. And we want to do that using 4 rectangles in the midpoint rule. Okay? Well, the way we're going to go about this is by first saying, you know what? I need to know what delta x is anyhow. Let's just go ahead and find that thing out. Delta x is going to be equal to b minus a. B in this case is 5, a in this case is 1, divided by the number of rectangles we're using. In this case it's 4. So delta x is just going to be equal to 1. Now, using that, what we need to do is we need to find out what our intervals are going to be. And our intervals are going to be from 1 to, we need to go delta x away. Well, delta x is equal to 1. So from 1 to 2, that's our first interval. Our second interval is going to be from 2 to 3. Our third interval is going to be from 3 to 4. And our last interval is going to be from 4 to 5. Now we're using the midpoint rule, so the particular x value we want to use is the x value that is dead ass in the middle of these subintervals. So we've got our whole big interval from 1 to 5. We're breaking it up into 4 subintervals. Each of those represent the width of one of our rectangles. Now we need to find the middle of each of those subintervals, because that is the x value we're going to use to find the height of our rectangles. Well, this first subinterval is going to have a midpoint at 1.5. The second one is going to be at 2.5, then at 3.5, and finally at 4.5. So now we're going to come over here. Let's go over here. And break all this up, or put all this together rather. So what we're going to do is we're going to say we want the sum from, let's use I again, from I equal to 1, my mistake, 0, up to 4 of f of x sub I, the midpoint, times delta x. And this thing is going to be equal to f at 1.5 times delta x plus f at 2.5 times delta x plus, oh, I forgot my delta x, plus f at 3.5 times delta x plus f at 4.5 times delta x. So that's it. Now we're going to go through and evaluate all this. Our function f here is the ln. So we could go one step further and actually start putting numbers in. F at 1.5 is just the ln at 1.5 times delta x. Well, delta x is 1 in this case, so we don't need to worry about it, because 1 times anything is just that anything, plus the ln of our next term is evaluated at 2.5 plus ln evaluated at 3.5 plus the ln evaluated at 4.5. And that's it. That's all there really is to this idea. The next video, I'm going to show you all how to evaluate these series with that limit to infinity attached. In the meantime, there is only one last thing I want to show y'all, and that's how these integrals, these definite integrals, interact with each other, what the rules are for their behaviors. And honestly, they're going to look familiar. I'm not going to lie to y'all, they're going to look familiar. Because a lot of the rules of calculus are pretty generic in that they keep reappearing in different forms. So you may have noticed this with limit and derivatives. You're going to notice this again with integrals. So give me just a second, I'll show you all. Okay, so the two rules that are probably going to look familiar are these two right here. The first rule says that the definite integral from a to b of k times a function integrated with respect to x is equal to k times that definite integral from a to b of f of x with respect to x. The constant multiple rule again, right? And that's all that is. Then there's this other rule that says the definite integral from a to b of f of x plus or minus g of x with respect to x is equal to the definite integral from a to b of f of x with respect to x plus or minus the definite integral of a to b from a to b of g of x with respect to x. Oh my god, that was a mouthful. Basically, it's the sum of difference rule again, right? Right. So these rules, these first two, pretty much mirror all the other rules we've seen before. Now, these three, not so much. Things get a little weird. This one, we'll see a little bit later on why it is what it is, and it'll make perfect sense when we do. But, till then, we're just going to see what they are. So this first one at the top over here is just saying that if you're going to integrate something from a to b, and there's a value c in between a and b, you can integrate that function from a to c and add that same, the integral from c to b and get the same thing. So here we're integrating from a to b, and we're saying that it's equal to the integral from a to c plus the integral from c to b, where c is in between a and b. That's all I'm saying. Now, the second one here, it's just saying if you integrate from a to a, your integral is going to come out to be 0. And if we stop to think about this for a second, it kind of makes some sense, right? Because we're talking about these things being equal to this idea of this rectangle, blah, 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 blah. We have this limit, and this delta x is equal to b minus a divided by the number of rectangles. But here we're saying b and a are the same value, right? So that's 0 divided by the number of rectangles. And it doesn't matter if you let the number of rectangles go to infinity or not, you're always going to be at 0. That's a constant value, right? And that's why this integral comes out to be 0. Now finally, this last one says the integral from a to b of f of x with respect to x is equal to the negative of the integral from b to a of f of x with respect to x. Now, later on in the class, I think in the next video actually, we're going to see that this is just because you're flipping some values. It's going to make perfect sense when we see that. But till then, this is something you're going to have to take at face value. Now, just thought it would be cool at this point to throw in some facts, some fun facts at y'all. Again, might be on the exam, I haven't decided yet. On the final, that is to say, I haven't decided about it yet. But you get this funny S thing, the notation, actually comes from the mathematician Leibniz, who is the discoverer, it would be the better term, the discoverer of calculus. Any of you who might be the physicist sympathizer and believe that Newton was the one who discovered calculus, you have failed. Don't show up, no, I'm just kidding. You haven't failed, but you're wrong. It was Leibniz. And the reason why he used this S was honestly just because he had no imagination. It was like, oh, I'm summing things up. Sum starts with S, and use that. Like that is honestly the at least the story that has been floated my entire life as to why that's the notation we used. But yeah, with that, I will let y'all go. If y'all have any questions, you know my email. Yeah. Email, office hours. But till then, have a good one, everybody.